Mohr circle. So the problem asks, determine the principal stress, which is A. So we're going to be doing part A in this video. The principal stress and the rotation to the principal plane, and it asks us to use Mohr circle. So what I'm going to do first, I'm just going to redraw the givens that we have. So what do we have? We have sigma x, which is the normal stress, and the x component of that, which is 120 megapascals. Just wait too. And then we have the vertical one, vertical direction, sigma y, which is what? The sigma y is 40 megapascals. Going down here too, same thing. And these, as you can see, they are going in the sigma x, sigma y, or in tension, which that means they're away from the block. So there are positive values, and we will discuss that soon. And for the shear stress, the orientation, I'll also be explaining that soon. So tau, which is the shear stress here, is given to be 60 megapascals. Alright. First thing is, I'm going to pick a face, and I'm going to call this the vertical face, and I'm going to call that one the horizontal face, H for horizontal, and this is what I mean by a face. So if I redraw, if you think, this is one way to think about it. Here's the cube or the square in 3D, right? For the vertical, when I call the vertical, would be here, so this is the face here, and there is the stress acting on that face, on the we can kind of call that a vertical face. So that sigma x is acting on that, right? And the one in the green, which I'm calling the horizontal face, is that surface right there. What is acting on that? That's sigma y. Alright. So I'm going to go ahead and draw the Mohr circle. So for the coordinate system, we have the vertical components, vertical coordinate system. So the vertical part, the vertical axis, is going to be the shear stress, and this is, I'm going to call this one CW for clockwise CW, and CCW for counterclockwise, and I'm going to explain that soon. And for this one is positive. This is just all the normal stresses that we have. So negative here, positive here. Now, for what does that mean to the tau? This is the method that we're going to be using for the tau going clockwise and counterclockwise. What does that mean, right? So we have our block right here. If we look at our vertical face, the shear stress acting on that face, if you think of the block having the origin right here, if you think that shear stress right here is making the block rotate which way? Is making it rotate clockwise, right? Because the force comes here and the origin is here, so it wants to rotate the block clockwise on that vertical face, right? So what that means is this, because now I want to plot I want to block the vertical face on my Mohr circle. So I'm going to have a circle. I'm going to have a center here. So I want to block V. I want to plot V, right? So V is just, I go in the x direction, the x coordinate system, which is going to be stress, I go 120, which is just the sigma x, and I go up by tau, which is just here is just tau xy. So if I were to plot v, would be somewhere here and somewhere here, right? So let's say v. So what's the x component? The x component is sigma x. So sigma x. So we come here, this is sigma x. We go up, this is tau xy. So that is going to be, the value is tau xy. Alright, so we have a center, as I mentioned before. Now, as you can see here, from here to here, there's the radius of the circle. So what is the problem asking again? We're trying to find the principal stresses and the rotation angle. So the principal stress is sigma 1, sigma 2. Those are the principal stresses, and then 2 theta p, we also need to find that, because we're going to be drawing that on another square, another block. Alright, so we plotted v, and then the opposite one would just be the h face. So let's go ahead and find what the center is. So what is the center? The center is the average, sigma average, which is just the average between the normal stress in the y and the normal stress in the x direction, which just is this sigma average, which equals, as I just said, sigma x plus sigma y divided by 2, which if you do the numbers, if you do the math, you're going to have 80 megapascals. Right? So for the radius, how do we find a radius for this one? Well, let's see. Let's find a radius. So we have here a right triangle, right? Here, here, here. So we have the x component, the y component, and then we have the radius, is what we were trying to find. So from here to here is what is just tau xy, because it's the origin. From here to here is just that value. The x component, however, is from here. You have to go from here to here, and this is the value that we need. This is the x component that we're looking for. So how do we find that? Well, this is one way to find it. Is we know this point here is v, so from here to here is v face, which is the x component of v, is what is just this sigma x. So from here to here is sigma x, but we can cut it right here by subtracting the center, which is just sigma average. So because we are away from the origin for the x-axis is right here, and we are all the way over here, so we have to account for this. So we have the x component is sigma x minus sigma average. Now, by using Pythagorean's theorem, we can go ahead and write and find out what the radius is. So the radius is what? is going to be the square root of sigma x minus sigma average squared plus tau xy squared, and that number is 72.1 megapascals. Alright, so yeah, so again, let's look what are we doing? We're trying to find out, this is the principal stress where it's going to be the highest, and this is the lowest. So this is the principal stress max, lowest. And I knew to draw my circle this way because the x component of the stress, thermal stress, is in tension, so it's going to be positive. So it's going to go positive this way, which is this value right here. And the same for my h, which is my horizontal phase. The stress is also in tension, which means that I'm going to be going this way. If it were negative, I'll be plotting a point somewhere here. But they're both in tension. The normal stresses are in tension, so we're on the positive side right here. All right. So, not necessarily for the principal, but you get the point. It would be somewhere maybe here or here. So okay. So we have the radius. Now we also need to find 2 theta p, which is that angle. So how do we find 2 theta p? Well, trigonometry again. So we got our circle. This is 2 theta p. Or our circle, our triangle. So this is 2 theta p. 2 theta p is what? 2 theta p is just the arctangent of this and this, right? Because the tangent is what? Opposite over adjacent. Alright, so erase that. Alright, so 2 theta p is the arctangent of the y component, which is just 2, not 2, but tau xy. And what's the x component? Well, as you can see, the x component of the triangle is just 6, not 6, but sigma x minus sigma average, right? So if you do those numbers, you will get, let me see, 56.3 degrees, and which means that theta p is just that divided by 2, which is 28 over 2. Alright, so now we almost have everything. Now we gotta find the principal stress here and the principal stress here. So principal stress 1. Stress 1. Okay, so how do we find that? Well, if we look at our Mohr circle, we can see that from here to here, looking at the x-axis, the normal stress axis, that's just the center, which is sigma average, right? Well, from here to here is what? That is the radius, right? So this plus this gives us this. So how do we find that? Well, that is just sigma average, which is the center, plus the radius, which if you do the math, you get 152.1 megapascals. And for sigma 2 is, if you go from here to the center, that's just sigma average. And if you remove that area, you get this, which is what we were looking for. So the center minus the radius is the principal stress 2. So average, sigma average minus the radius. If you do the math, that is going to give you 7.9 megapascals. Okay, so now we actually have everything we need to answer A. So let's go, but we still gotta go ahead and draw the block. Now let's go ahead and draw the block. We have the x coordinate or y coordinate, x coordinate. Now, what we're drawing now is the block for the principal stresses, which here and here, right? From our vertical face to the principal stress number 1, we go from V to principal stress number 1, which is the maximum. We go from there to there in a clockwise fashion because we're going from here to here, right? So this is the initial, final. That's clockwise. And we go from there to there. From what angle? The angle of 2 theta p, right? If you look at the Mohr circle, but when you go from the circle to the square, 2 theta p becomes theta p. So this is what happens. So we're going clockwise from here. From the circle is from V face to there, from there to there, counterclockwise at that angle. From here we're going from the x, from the reference, clockwise at an angle an angle of theta p. And we have all the values. You can just put in the values. So we go from that angle to that. And this is what the block is doing, because this is the vertical face, this is the principal stress, so this is the vertical face, and this is the horizontal face, right? So in relation from the vertical face in relation to sigma 1, we went from here to there in a clockwise fashion, and that principal stress is what is in tension, is positive number in a positive axis. It is what, well, we already calculated that. Whatever that is sigma 1 from here to there, sigma 1 acting on that vertical face, because sigma 1 is acting on from here to there. All right. The vertical or the horizontal face is going to be which is going to be over here, just the opposite way. And we already calculated, which is just going to be, it's the same angle, 2 theta p over here. From here to here is this value, so the horizontal face is sigma 2. So that's it for that problem.